Starting in section 1, everything about troubleshooting switches and ladder diagrams and stuff. The biggest deal is relays, contactors, and motor starters. These are all essentially the same thing. I try and keep them all as the same thing in my head. Basically, anything that's a switch, I just try and think of it as a switch in my head, and that's a lot of your control devices, really. Some of them are going to be temperature switches, like high limits or rollout switches, or basically any safety pressure switches. Just a switch, right? Some of them are going to be automatically controlled by coils, right? So they're magnetically controlled. So you have two connections. You have the control side connection and the load side connection, whatever that may be, even if it's still on the control circuit. But when I'm trying to troubleshoot, I generally just think of all that stuff as switches. A relay is a switch, contactors a switch, thermostats are just switches. It helps me not get too bogged down with what exactly it is. The biggest deal on the relays, and I know I mentioned it before that you should probably look at it, but the biggest deal is to make sure that you understand, the difference between a single pole double throw or a single pole single throw, and or 3-pole double throw. You're gonna have, if it's single pole single throw, you basically have an off and an on position. If it's single pole double throw, you'll have a normally open and a normally closed position. Generally speaking, depending on how the switch is set up, it can be a little bit different than that. It'll be single pole double throw, but you could still have an off position, but it's still double throw because the off position doesn't really count most of the time the way they name them. All right. But if there's a set of contacts that it can connect to, that's one throw. And you need to make sure that you got that kind of straight in your head when you're looking at it, because you need to be able to figure out what position is normal and what position isn't normal. And remember, normal is what it's doing if it's sitting in your hand, right? The normal position of something is what it is if it's not connected to the circuit and no power is applied to it, especially if it has a coil in it, then it not being energized is the normal position. And generally speaking, switches are going to fail in the positions that are that they're naturally at. So if the switch is closed almost all the time because it never opens up, then a lot of times it's going to fail in that closed position. The only difference being bimetal switches like motor overloads and things like that, because that metal tends to fail as it expands to break the circuit. Those tend to fail in that open position if they're overheating a lot, because the metal doesn't go back to the position it was very well after a lot of cycles on it. So just something to keep in mind. But relays, contactors, even motor starters, the only difference with between a motor starter and a regular contactor is they'll have some kind of overload on it. But these are all just switches. Time delay relays, it's just a switch that works after a time delay period. Going through compressor short cycle timers, those are compressor connectors. It's basically just another type of time delay relay. Most of the ones we deal with now aren't all mechanical. Most of those short cycle timers are built into boards and things like that. Lockout control relays and circuits, I know we touched on a little bit. You really don't see those that often anymore, at least from the factory. They're nice relays to have. And it's really something that's a good idea to add. I think I mentioned it before. When you are, give me just 1 second. Sorry about that. But anyway, I know I mentioned before that when you've got something that trips on high pressure, you got an RTU, especially as it's getting old, and it tends to trip out on high pressure. Or even if it's not that old, if it's had some issues before where condenser motors are failing or something, you'll see situations where those high pressure switches, they just open and close a little too fast, and it ends up short cycling the compressor. So if you've got some kind of lockout relay in there, then you can stop that short cycle by making it lock out, so it has to be manually reset by cycling power. So it's a really good thing to think about adding into a circuit if you're on your safeties. If you notice that the safeties tend to short cycle under certain circumstances, or if it's got a problem that you're trying to figure out and diagnose, but it's causing a short cycle in the system, anything to keep that from coming back on after you have an issue is an excellent way to try and protect that system from other failures related to, it's a shame when a compressor gets killed because a condenser motor failed, um, because it trips out on high pressure, that automatically resets, and then it trips out on high pressure again or something like that. And you can fix that with manual reset switches and things like that too. But a lockout relay is a good way to make sure that if anything in that circuit fails, and if any of those switches end up tripping, then you've covered all of them. So, something you should really keep in the back of your head when you're diagnosing things or something, it's a really good, um, it's a really good professional way of adding a little bit extra insurance to a system relatively cheaply. And with that in mind, um, remember that if you read through lockout relays and control circuits, all right, the only way to reset that relay is generally to cut the power to the control circuit. If you interrupt the control circuit power, that'll reset the relay, and then when you turn the power back on, it'll operate as normal until it trips again. And that's how they work. It's based on a high resistance in the coil that does not energize unless the power gets cut through the rest of the circuit, and then that high resistance coil will have enough power fed to it to close, and it basically holds itself closed until you reset the power to it and get it to feed something else again. So 1.1.4, I want you guys to make sure that you understand that section and make sure you understand lockout relays. All right. A typical relay with normally closed contacts, um, typical relay with normally closed contacts is something that you get a question on. I'm not sure I love the question, to be honest. All right. Um, oh, I see what they're saying. Okay. So when you've got normally closed contacts, it is something important to understand. So I'll give you my favorite example of a relay with normally closed contacts real quick. My favorite example of a relay, what to use the normally closed contacts for, is a fan relay inside of a heat pump, an air handler or something like that. And typically on a heat pump on the electric heat side. So um, when you've got a fan relay, there's two things that a fan relay really does when it comes to an air handler or a heat pump. All right. The fan relay in there is there as a time delay, and that's just to kind of boost the efficiency of the system. So as it shuts off, the fan runs a little bit longer to extract that last little bit of heat and that last little bit of AC out of it. I believe they'll tell you that it's there, to keep the electric coils cool as it shuts down. But in my experience, it's not really necessary. Those electric heaters tend to cool down enough. Um, just naturally that I don't think that that's really an important aspect to it. Its main thing is squeezing a little bit more efficiency out of the system. Um, but if you have a bad um, if you have a bad fan relay inside of an air handler, okay, you can that little circuit board. It's generally that little circuit board in there. You can replace that with just a um, hmm, give me just seconds. Somebody's texting me. Yep. Oh, okay. Dang it. Uh, Whitner, Jeffrey Whitner. I'm sorry, buddy. I did not see the waiting room. I didn't have that up. I had another screen open. I really wish it would do something to alert me when someone's in the waiting room. I got to figure out some way to do that. Um, so I guess just to bring you up to speed for a minute, um, I want to make sure you read 1.1.4 on lockout relays in your book. That's the main thing we've talked about so far. So make sure you read that section. All right, going back to normally closed relays. My favorite example of normally closed relay is when you've got that fan board inside of an air handler. You it's got a normally closed and normally open position on that in that fan circuit board. Besides serving as a time delay, you have a normally closed and a normally open set of contacts. The normally closed, the power is backfed from the electric heat so that if for some reason the fan doesn't come on, but the electric heat is energized, the fan will automatically come on as long as it operates so that you don't burn up your heating coils on accident. All right. So the whole idea is that if you feed those electric heaters, you automatically power the fan no matter what. The normally open set of contacts gets fed from your G terminal and the thermostat, and then when it energizes, it powers the fan. So that normally closed position is generally there for something that you either want to have running or as an extra safety um, in case you have an issue. So your exam is going to ask you about typical relays in normally closed positions. What kind of purpose could those contacts perform? And generally, it's not going to be something that's going to power a device. It's going to be something that's going to either be used as a safety or to de-energize something that doesn't need to be energized when the system is running. All right. So keep that in mind when you see that question. I would read through 1.1.1 to make sure you get it. But like I said, it's generally going to be some kind of safety or it's going to be some method of de energizing something that doesn't have to be energized during normal operation. Um, I'm trying to think of another example besides the actual answer. But just remember that note, or like I said, read through it, um, and you'll get the answer. But yeah, it's generally not going to be starting a motor. It's not going to be starting a compressor. You're not going to use normally closed contacts for that a whole lot. There's very few cases in which you want that normal position to be energizing something. But uh, yeah, it yeah, like I said, I can't think of anything, but it'll de-energize something. Well, no, that's still energizing something. But regardless, it's going to be some type of safety or something that doesn't need to be on when the system's normally operating. So it's not going to be starting up a inducer or compressor or any part of a motor or anything like that. It's generally going to be a backup for something. In weird things can be safeties, you know what I mean? Weird things could help. You don't think of them as safeties, but they are because they're there just to protect something. Um, what else in relays? They go through pressure switches in here, freeze stats. Again, I just think of all these things as switches. To me, a pressure switch, a freeze stat, an outdoor temperature thermostat, just kind of skipping, passing through the sections. Um, all those are just different ways of turning a switch on and on, just different ways of doing it automatically. You just have to understand the temperatures or the pressures at which those operate so that you fully grasp the operation of them. Furnace fan controls are basically just time delays. That is a good example, actually. A furnace fan control, especially the old school ones. That is a good example of something that starts in the normally closed position to power a fan. Um, because typically, if a furnace fan, I don't know if you've noticed, especially, I haven't paid much attention on the new ones, but even a lot of the newer furnaces, it's the same way. Those are fed off of a kind of a normally closed, normally open set of contacts for low and high speed. So a lot of times a furnace fan will come on as soon as you turn on the system for a second, and then it'll shut down as the time delay kicks in. And the time delay is actually what keeps that fan from running. So that time delay has to be energized for a split second before that circuit has to be energized for a split second before the time delay opens the circuit on the fan. So that's why that's generally how you can tell if the fan control is no good. Is you'll turn it on and the fan will just keep running. You don't see that initial bump and then it shuts off. Um, as soon as you power that system on, the fan just runs. Because even if you're powering it in heat, as long as you don't have the fan in the on position at the thermostat, the fan will bump for a second, and then it'll go through its heat cycle, and then after the time delay, the fan will come back on. So that's kind of a good way to spot there might be an issue with the relay on the circuit board for a furnace fan control. Limit controls, all your limits are just bimetal elements. Basically, your rollout switch is really just a temperature operated switch. Your high limits are just temperature operated switches. And bimetal is a good thing to kind of understand because, like I said, they tend to fail in the open position. And that's actually the next thing I want to go over. So, when you're talking about temperature switches, motor overloads are a temperature switch. Your a lot of times even thermal overloads will tend to be temperature switches. High limits are just temperature switches. These are all just temperature, usually bimetal switches. And older thermostats, older room thermostats are just bimetal switches. So they've got a couple different designs. It can just be basically a strip of metal. That's pretty springy. And there's two different metals there that expand and contract at different temperatures, so that as power's passing through it, if it's kind of an overload, or as it heats up, the one metal expands and it breaks the switch, and then when it cools down, it closes the switch again. That's basically how a lot of your even your like your breakers essentially work, is that bimetal element in there that just opens and closes, and it's just two different metals so that it kind of sits, and I forget what they are, but it kind of sits in a normally closed and a normally open position. The other one with room thermostats, and this gets into module 2. So looking at furnace limit controls, bimetal switches and stuff there, near heat exchangers, and then combination, well, yeah, still combination fan limit switches. So this is page 11, 1.2.5, 1.2.6, and bleeding into room thermostats in 2.1.0. read through all those a little bit, but what I want you to get out of it is you can have the bimetal spiral wound switches if you and you get a good picture of it on page 14. And all that is that same design, two different metals kind of permanently attached to each other in a spiral position. And hmm? In a spiral position, and as it heats up, it tends to turn, right? So if you've ever looked at an old mercury thermostat with that bimetal on it, you can see where the mercury switch, as the metal heats up, it tends to spin, right? Because it's spiral wound, and that's what makes or breaks that little mercury switch on the inside. And that's why they used to have to be level. Your old thermostats, your mercury thermostats had to be level because that tube of mercury is basically all that made or break that switch. And if it wasn't level, it would be at the wrong temperature when it made and it broke. And if any of you guys do any plumbing, a lot of your mixing valves and stuff operate the exact same way. There's a big bimetal spiral wound thing in there, and that bimetal spiral wound element moves a valve back and forth to try and maintain temperature in the pipes. So as the temperature changes, it reacts and moves the valve to try and meet basically equilibrium of where the temperature setting is at. So it's really neat to understand how those things work. And where this is kind of a tangent, but where I kind of link everything together in my head is on pressure, not pressure, yeah, on pressure are gauges, right? On pressure gauges, it's basically just a coiled tube that as the pressure goes in, it moves the gauge. So the spiral wound or the circular design of something is real good to actuate other things. And so just remember those bimetal elements in room thermostats that are spiral wound or those circular designs help control things in really elegantly simple methods. You know what I mean? The design of all your old mechanical stuff is really cool. So just understand that that's how old room thermostat works. These days, it's, all thermistors and electronic relays and stuff, but that's how those worked. And remember the bimetal switches, the one downside to them is obviously it's a mechanical device. So as it actuates or as it turns, it tends to break down over time and not be as accurate as it used to be. Or in the case of bimetal overloads, as it actuates a lot, it's kind of snap action. So that's how a compressor overload ends up sticking open essentially, is because that bimetal is stretched so many times it gets to a different position and it just doesn't want to move again because it's, at that point the metal is fatigued. So there's that. Moving on again, as section, we're in module 2 now, right? Or section 2 of module 2 now. So it goes through heating only thermostats, cooling only thermostats, heating and cooling thermostats, and then automatic changeover thermostats. And once you get past heating and cooling only and you start to get to well, no, not really. Once you get past just heating cooling thermostats, you get into auto changeovers and multiple stages and programmable thermostats. This all gets out of the bimetal realm, mechanical realm, and into the digital realm. And actually, I had a lot of fun last night. Give you guys a quick story. I had a lot of fun last night working in a commercial building where there's 3 thermostats on the wall, right? Oh, we got another guy waiting. Had a lot of fun last night going over a commercial system. I want to say the system was late 70s, where I was changing a thermostat out on it, and the system is water source, cooling only unit, a duct heater for heating, and there's 3 thermostats that controlled it. You had a thermostat for just cooling, a thermostat for just the fan, and a 2-stage heating only thermostat. And based on what I saw, how they set it up, it looked to me, and I could be wrong because I didn't dig into the thermostat that hard, but it looked to me what they did to make the 2-stage heating thermostat was they somehow rigged up a heating slash cooling thermostat as a 2-stage thermostat, because everything on that thermostat was labeled as if it was a normal heating cooling thermostat, an old school one. It took me a long time to figure out what they did to rig all that up to basically make some stages out of this thing. But that's what they did. So, I guess, you work with what you got back in the day. But nowadays, it's a lot easier. You just have the multiple stages set up. One good way to create different stages on heat is outdoor thermostats, right? That was the old school way of making multiple stages of heat. You'd have a single stage heating thermostat, but you'd power the other stages off an outdoor thermostat. So unless the temperature dropped below a certain degree, you wouldn't kick on the extra stages of heat. We still do that a lot of times with hybrid systems nowadays, right? You uh, you don't let the you don't let the furnace kick on. You use the heat pump until it gets below a certain temperature, and then you let the furnace kick on. We still do it a lot with boilers. You'll use outdoor temp sensors to do outdoor reset on boilers, right? But back in the day, you'd see, if you did higher end houses and stuff with multiple stages, the guys used to use outdoor thermostats all the time to control the stages to try and save energy on a system. And that's how you do it. And it's really not, there's still instances in which that's a good way to control electric heat to stage it. But moving on, when you get into when you get into digital thermostats, okay, you get into digital thermostats, now you need to understand thermistors, okay? And thermistors, all a thermistor is a device that as the temperature changes, the resistance changes, okay? So the way a circuit board interacts with the thermistor is generally it's going to send it 5 or 10 volts DC. All right. It'll send out 5 or 10 volts DC to that thermistor. And because the resistance of that changes with temperature, you'll have a voltage drop. If you remember anything you did on Ohm's Law, did you guys learn Ohm's Law in the last couple years? I assume. Hopefully. Any takers? I can't hear crap. I saw you talk, dude, but I couldn't hear you. All right. I don't know what's up there. But anyway.
Yes, we did.
Okay. So you know that the most basic, remember, Ohm's law is good for understanding anything that's not an inductive load, right? Using the rules you learned for Ohm's law works really well for any resistive load. Inductive loads like motors and everything get more complicated, but you can predict voltage drops across any resistor by just following Ohm's law. And that's all the circuit board does. It sends out a signal to that thermistor at 5 or 10 volts DC. So say it's 10 volts DC. And then if it comes back at 8 volts DC, it knows essentially what the temperature is because that resistance dropped the voltage by that much before it came back to the board or before it went to the other device, because you can use a thermistor to say, I think we discussed it briefly, control an EEV just by making the EEV open and close at the right voltages, matched up with the thermistor. Okay, so all it is something that changes with resistance with temperature. Something to remember about thermistors is there's only really a few different primary resistors. I mean thermistors that are used. I'm sure there's tons of designs out there, but there's really only a few curves that are very common. And so you can basically order a big bag of thermistors off of Amazon, and if you get the right one, you'll end up with something that'll replace half the thermistors you run across, whether it be on an RTU or whatever. And then if you grab a couple bags, you'll have most of them for any situation because they all tend to work around the same curves. Um, so there's a few that are pretty common. Doesn't mean you'll have all of them covered, but you'll have a ton of them covered. And even if it doesn't work, it'll usually get you a system working until you can get the factory thermistor. But your primary types are positive temperature coefficient and negative temperature coefficient. So on a positive temperature coefficient, the temperature as the temperature goes up, the resistance goes up. Okay, so it's the same. It's positive just means that they kind of move together. Okay, so as the resistance goes up, as the temperature goes up, the resistance goes up. As the temperature goes down, the resistance goes down. That's a positive temperature coefficient. A negative temperature coefficient means that as the temperature goes up, the resistance goes down. As the temperature goes down, the temperature goes, or as the temperature goes down, the resistance goes up. So they move opposite. Okay. So positive temperature coefficient thermistors, as each changes, the changes are the same. With a negative temperature coefficient, as they move opposite. So as the temperature goes up, resistance goes down, and vice versa. So you need to remember that, and you need to, if you look on page 19, it goes over. It has a thermistor curve in there, and that's what you're looking for when you're troubleshooting thermistors. Is you need to see that curve so that you can figure out whether the temperature lines up with the curve. But I'll tell you this. I can't think of one time where I've had a thermistor that wasn't either shorted, open, or working. It's pretty rare, extremely rare that you're going to have a thermistor that's just out of whack. You know what I mean? That, it's the temperature is, if you look at this curve, the temperature is 32 degrees and the thermistor is supposed to be at 33,000 ohms. And it's really at 60,000 ohms, even though we know the temperature is 32 degrees. It's not out of calibration very often. Generally, it's going to either be shorted, it's going to be open, or it's going to be operating properly. Doesn't mean you won't run across that sometime, but it's pretty rare. Thermocouples are one thing that can be kind of out of calibration pretty easy. I've always liked having a meter. If I'm using thermocouples, I like having meters where I can calibrate the thermocouple because they don't all seem to work exactly the same. They're not super accurate. They're pretty accurate, but thermocouples don't tend to be super accurate. Thermistors tend to be a little bit more accurate. They tend to follow their curves pretty well out of the box. So in general, if you're troubleshooting a thermistor, it's going to be either failed or working. Doesn't mean don't double check sometimes that it's good, but I can't think of the last time or any time off the top of my head right now where I found a thermistor that just wasn't quite in calibration, like it was just acting funky. But the main thing I want you to remember there is that the difference between a positive temperature coefficient and a negative temperature coefficient. All right. Thermostat. All right. I'm not A thermostat, you should know. If you do not know, read about it some more. I mean, if you don't work with a lot of thermostats, maybe it's not ingrained in your head, but you should know what the R terminal is for, what the C terminal is for, what an O or B terminal is for, what W1, W2, Y1, Y2, common, or C. All these terminals on a thermostat you should understand. If you don't, go out and buy a cheap thermostat, cheap heat pump thermostat, or one that's conventional or heat pump, and read the manual and keep it next to you until you kind of got it ingrained in your head. The other thing I'll tell you is try and come up with a um, color system that works for you. And most of them are the same all the time, right? R is red, um, Y is yellow, G is green, um, W1 is white. But when you start getting into W2, or you've got 24 volts for heating and 24 volts for cooling, you've got separate power wires for those on like a boiler system or something. Little things like that. Try and keep something in your back of your head that works for you every time when you wire it, so that you know what each wire color is when you look at it most of the time. You're always going to have situations where you got to switch out a wire or something, but like some people use black for common, some people use blue for common. Um, Sometimes brown is common, but you got to come up with something that you do it the same way almost every time, so that when you've done the system, you can remember exactly how you hooked it up if at all possible. And a lot of times that's going to be matching up how the equipment manufacturer does it, because they'll have certain colors coming out of the units. So you end up using those and you get used to that way. But come up with a system that always works for you and try and keep it the same for weird situations when you got multiple stages of cooling and heating. And use lots of wires, at least 8 wire, if not 10 or 12 wire or something, so you got plenty of colors to work with for weird situations. But on the other hand, understand that other people might have the same weird method of doing those same situations. So don't automatically assume just because it's this color, it's that thing. When I was talking about that commercial system I had to figure out and put a thermostat in, and they use 3 thermostats for what you can now do with 1 thermostat. One of those thermostats was really just controlled the fan, but it was labeled as a night cooling thermostat. So in other words, unoccupied cooling. This was the thermostat to control the temperature there. And it was a G wire. I did not take it for granted that was a fan, because I'm sitting there thinking, well, it's probably a different stage of cooling or something. Just because it's green doesn't mean that's what it was for. Lo and behold, that's what it was for, is just a fan on a thermostat. But don't assume just because it's G, it's fan. Don't assume just because it's white, it's heat. Make sure you know for sure what it does. But you should still have a system that works for you, so that you don't get confused when you run into, a weird situation where you need multiple wires for the same purpose. What else? If you're trying to troubleshoot a thermostat, a method a lot of people like to use, and I actually don't use it very often, and I want to say we went over this too, but jumping terminals at the thermostat. It's a good way to figure out if you've got issues at the thermostat itself, but if I'm jumping terminals, I'm going to do it at the indoor unit or something, or the outdoor unit. That's where I generally jump things to mess with it. It's been a very, very rare situation where I had to actually jump those terminals at the thermostat. I don't know why I don't like it. I just don't like messing around with the terminals near the thermostat unless I need to redo them or something. But it is a good way to determine, okay, is my signal going to the thermostat and back from the thermostat to the unit? And it's important to recognize, that wire might be messed up coming back from the thermostat. And if you need to determine that, then you need to jump those wires at that location to figure it out. So, along with understanding, okay, what those different terminals are for, what R is for, Y is for, W is for, G is for, so on and so forth. Understand that if you're going to jump them there, you have to get power from one to the other. So generally, you're going to be jumping R to something else. Jump R to Y, R to G, R to W, whatever. So as long as you know what each terminal is for, you know which one to jump. Beware. Interesting. If you ever jump R to G, okay, sometimes that'll kick on cooling, depending on how old the thermostat is and how it's set up. Jumping R to G can activate cooling because in auto, a lot of times it's normally closed to cooling internally in that thermostat. Again, depending on the age and model of the thermostat, don't be surprised when that happens. Jumping R to Y, same thing. Sometimes will power G, whereas it won't with like R to W. So if you're testing heat and jumping it out, you'll need to jump out R to W and R to G. But jumping R to G, you might not have to jump R to Y. And beware if that happens in case, if in case you jump R to G and you see cooling come on, don't assume there's an issue. That could be normal depending on what the thermostat is. So don't get surprised when that happens. The last time I had that happen was probably 6-7 years ago. Brand new thermostat, digital thermostat, cheaper but normal digital thermostat. It would still kick on cooling if you jumped R to G. So it's still something that occurs. So don't assume that you've got an issue when that happens. Just a note to keep in mind. All right. We use 24 volts in control circuits. All right. This is getting to section 3. All right, let me see if there's anything else in section 2 I wanted to talk about. Goes through adjusting heat anticipators and stuff. I think that's basically outdated at this point. Unless you guys can give me a good example of when you should still be able to adjust a heat anticipator, I don't want to discuss it because I've never had to do it. Never. I learned how to do it when I was in school, and your book tells you how to do it. And if you need to adjust the heat anticipator, get a digital thermostat. You guys know you have to dispose of mercury properly. And then it goes through thermostat troubleshooting, and it goes through all that jumper stuff we just talked about. So section, basically everything in section 2.4, you should understand on thermostat troubleshooting. And I guess the only other note I'll add real quick on thermostat troubleshooting is that 9.5 times out of 10, it's not the thermostat. I think I've only ever found 2 actual failed thermostats, and I don't know how many times I've had somebody tell me, "Oh, I changed the thermostat and I still had the same problem." It's because thermostats are pretty reliable devices. Someone got kicked again. Yeah, I guess if you get kicked, guys, make sure you text me because I'm not paying much attention to the waiting room because everybody's here. But anyway, I don't know how many times I've heard somebody talk about changing out a thermostat and still having the same problem they had before. And I can count that on more hands than I need to count how many times I've actually run across a failed thermostat. It does happen. Don't rule it out. But assume it's probably not the thermostat, and you should probably be checking everything else first, which again is why I don't jump wires at the thermostat often. Generally, if a wire's broken, I can figure it out by the way the voltage behaves, and it's pretty rare that you actually have an issue at a thermostat. Modern digital thermostats are pretty damn reliable. I'm sure there'll be situations where there's a batch of thermostats from whatever manufacturer and they have a tendency to fail. That's always going to happen with all devices sometimes. So, next week there could be 1,000 bad Honeywell thermostats. As a matter of fact, somebody told me they had issues with a particular Honeywell thermostat failing, and I know for a fact that one is really weird. It is the T6 series. I know guys who really hate those, but it's because you got to wire heat pumps funny on them. You got to pay attention to the directions. But somebody else told me that they had a lot of bad ones, and I tend to think maybe they're just wired funny, and they're not wired properly because they're funny about how you wire heat pumps on them. But other than that, I mean, how often? I mean, you guys will still see them if you do any residential. I think most of you guys don't, though, right? Most of you guys don't do residential, but even commercial, they use them sometimes. Those old Honeywell Chronotherms from like the '80s. Um, they have issues with storing memory and crap in them, but for the most part, those things still work. It's pretty rare you take out a thermostat because it's bad. So I don't know. I guess the only thing I'm getting at is it's probably not the thermostat that's the problem. Rule out as much other stuff as you can before you assume the thermostat's the issue. It could be, but it's probably not the thermostat. All right, what else we need to go over? Oh, 24 volts. 24 volts being used in control circuits. So getting to page 30 on section 3, 3.1. It's going over control circuits and 24 volts. There's a couple reasons kind of the industry's mostly 24 volts. We use 24 volts not only because of electronic components. Electronic components tend to be low voltage. The way they try and set up electronic components so that they work well on low voltages, so that batteries can be put in them, and it doesn't take a lot of you have to use 20 freaking AA batteries to power something. So that's one reason we use low voltage. The other thing is safety. Generally, it's a bit safer to handle low voltage. You're not as likely to get shocked, but you still can get shocked by 24 volts. All right. So don't assume. I mean, I don't know if you guys have ever had it happen, but I have had it happen where I was pretty wet. I'd been I think out in the rain or working on something, and you grab that low voltage circuit to do something and you get a little bit of a tingle and it'll surprise you. So, anything that lowers the resistance of your skin if you're wet or something like that, you can still get a little bit of a shock from 24 volts. So it can still shock you, but it's not quite as dangerous generally speaking. But the main reason is it allows us to run it when you get into high voltage. Technically, you're supposed to be an electrician to run those, and that's I think that adds to the reasons, even though it's not. I don't think it's anywhere near the primary reason, but I think codes do add to it. But we use 24 volts mainly because these things are easy to install and easy to mess with, and um, it's less of a headache using higher voltages. And really, a lot of the electronic components are made for those lower voltages for a ton of industry reasons. But It's mainly just because it's easier to install. I guess the components are easier to install is the biggest reason. The circuit components and everything are less expensive, um, and it's a little safer, and it's more compatible with electronic circuits. Even though a lot of times that 24 volts gets turned into 10 volts or 5 volts DC on your thermostat when it's powering it, they just switch that voltage down even more if you're not using batteries. But yeah. All right. What's next? We go through. We were talking about the fan relays, and this gets into heating and cooling system sequence, which I think we covered pretty well, right? We covered sequence. No, if you guys watch my other video on it, I told you guys I put that other video up on the other class, and I think I added to our class YouTube list too a while back. I did I think, a better presentation of sequences of operations than we ended up getting during that class. So it's something I recommend you check out as my few videos on sequences of operation. So yeah, I remember when we looked through that, I wasn't in love with the way the book presented it as I actually went through it, but we still covered sequences of operation. So this goes, the next part goes into heating and cooling sequences of operation. And on the cooling sequence, there's something in here. I'm trying to figure out how I want to go over it. What does it say? Oh, so yeah, it talks about some of the stuff in the sequence on your exam, but the biggest thing is it asks about using separate sets of contacts on a fan relay. And here's another question I don't really like because it depends on what you're talking about. And yeah, it's not quite right. All right, so remember on an air handler, like I said, remember that on an air handler, you generally have a normally closed and normally open set of contacts as a backup safety in case the electric heat comes on and the fan's not in the on position or the thermostat didn't energize the fan or whatever. Because you can do that. A lot of thermostats, you can set it up so heat is energized by the equipment because that's what furnaces do. But if you hook that up to an air handler, the equipment a lot of the times won't control the heat coming on. So you can end up powering heat without powering G if the thermostat's weird or funky or set up wrong or something like that. So that's what it actually does in most air handlers. But on your exam, it gives you another reason, but it's equally important to make sure you understand. When you have separate sets of contacts on a fan relay, the other reason you'll have that is because if you remember when we talked about motors, one thing that's very important with motors is you cannot energize two speeds at the same time. So if you're setting up multiple speeds for whatever reason, say you wanted to have an air handler that had a lower speed for heating than it did for cooling, and you were going to set this up yourself. You need to interlock those speeds somehow so only one can come on. You don't want to have a relay for high and a relay for low, two separate relays that could somehow, when something else fails, energize two speeds at the same time because you're going to burn the motor up like that. Okay. So in general, if you're going to have separate fan speeds, what you would do is end up going into a fan relay, like, if you've got any safeties on it, and then you'll go into another normally closed, normally open relay that'll energize only one speed at a time. Because a double pole relay isn't going to get stuck in both positions. I don't know. I've never seen a situation where that mechanical relay can get stuck in the normally closed and normally open positions. If it's got an off position, it can get stuck there, but it doesn't get caught with both contacts energized at the same time. It's almost impossible unless there's some heavy damage to that relay. So, in general, if you've got multiple speeds on a unit, you want to control those by a single relay so that only one speed can get energized at any given time. All right. It's very important to keep in mind if if you've got to set something up weird or something like that. Now, nowadays, you've got ECMs. Most everything is going to ECM over X13s basically over the next couple years. All right. They're gonna get all our PSC motors and units are gonna get phased out for ECMs because the ECMs are at least 20% more efficient. So, in the interest of saving energy and everything, you are not going to see PSCs and newer equipment for a whole lot longer. Maybe still inducer motors for a while and things like that, but not your blowers. But on an ECM where you've got the control signal that dictates the speed, it's no big deal if you have both powered at the same time because that controller inside the motor is going to know to only set one speed at a time. It's not the same as sending high voltage to two separate things. That there's not multiple windings in an ECM that you have to worry about. But if you got multiple sections of winding, right? Remember, a PSC motor, it's just one winding with multiple taps in it. If you've got multiple taps on a winding, you can't energize more than one of those taps at a time because the thing will burn up. Same thing with the transformer, right? If you got a multi-tap transformer, you don't want to power it across 120, 208, and 480 at the same time because you're basically just creating a short when you do it. If anytime a winding has multiple taps, if you put power across more than one of those taps, then you're going to burn it up because you're just creating a direct short from one tap to the next one. So that's what you'll need to remember for your test as far as relays. So understand those are the two functions of a fan relay, having two sets of contacts, and you won't get asked about the time delay one. You'll be asked about the motor speeds. Pneumatic controls. We did not cover pneumatic controls at all. All right. I didn't talk about them very much at all. I've worked on pneumatic controls a couple times. They're not very complicated. You're basically just using air pressure to move switches. So basically, everything in a pneumatic system is some kind of pressure switch. What made pneumatic systems very popular and nice in commercial settings for a long time was we didn't have DC controls that could modulate, but you can modulate something with pressure. It's very easy to have a valve that opens all the way at 30 psi or whatever the pressure is, you know what I mean? Opens all the way at 30 psi, is closed all the way at 0 psi, and you can pick a position in between just by changing the pressure going to it. So if you send it 15 psi, it'd be half open. So that's what made pneumatics so popular, is there was a time period there where we didn't have modulating electrical, but we could do modulating with air, and air is extremely good. Pneumatic systems, fluid systems in general, are extremely good at regulating something. The reason we're all heavy equipment is hydraulic. All right, all heavy equipment is still hydraulic because you get a lot of force and you get a lot of fine movement out of moving a fluid to move something else. So it's an extremely good way of handling that situation. Whereas, if you wanted to run something like a backhoe or an excavator off of all electric motors, we can do that now, but you're going to have a lot of different motors and they're going to have to be very strong motors. And you can do all that with a lot less effort by using a fluid as your medium to control everything. So that's what made pneumatic controls popular. So, the pneumatics aren't something that I can talk about right off the top of my head, and I don't necessarily expect you guys to either. If you ever get a chance to work on a pneumatic system, kind of try and understand how it works because it's pretty neat. And I would really recommend you read through this section on pneumatic controls because you'll still run across them in some commercial buildings now and then. Um, I worked in buildings where they're slowly moving over to all electronic controls, but there's still some pneumatic stuff left over. Um, I've seen a reasonable amount of them in Fort Belvoir. I've seen them in a couple older restaurants. So you will still run across pneumatic controls. You'll still have to be able to find pneumatic devices sometimes to replace them. And your best bet is generally the internet and trying to get as close of a direct replacement as you can. And there's a couple websites. It's been a long while since I had to find them, but there's a couple websites that still specialize in that, and you can call them and get the right equipment for whatever your situation is by explaining them what you have. It's kind of a really niche industry where the guys that know about it really know their stuff. But I would read this section on pneumatic controls in your own time, read over the basic components and how they operate, just so that if you run across it, you're not completely dumbfounded. But they have kind of the same situation as thermistors. Remember, we were talking about negative temperature coefficient and positive temperature coefficient resistors. You have direct acting thermostats in pneumatics, and you have reverse acting thermostats. So one of them will change as the temperature goes up. The pressure goes up in the system downstream of it, and that'll move a damper or whatever. So as that pressure runs through the thermostat, as the temperature changes, it'll increase or decrease the pressure going to it, which is going to change the pressure and whatever it's controlling. Whether a lot of times this is going to be like chilled hot water, and it's going to be controlling a valve. So as the temperature goes up, the pressure goes up, which opens the valve more, which allows more chilled water to go through the coil, right? That would be direct acting. Then you can have reverse acting, whereas the pressure goes down, or as the temperature goes up, the pressure goes down, and then that valve closes more. And you may want that for if your valves normally open the other way, right, or normally close the other way. So you might want it to reverse act if that valve's normally closed and you want it to open up or whatever the case may be. So just remember there's direct acting and reverse acting thermostats. And a lot of times with pneumatics, what you need is pretty important because it's going to change how those valves open and close. And again, I'm trying to think of a situation where a pneumatic wasn't a chill hot water like hydronic system, and I can't think of one. Doesn't mean they're not there again, but again, it was a good way to control valves more than anything else and modulate valves. So that's typically what you're going to see if you're dealing with pneumatics. So yeah, make sure you understand how those thermostats work and what is direct acting or reverse acting. Okay, good. I thought I told you guys wrong there for a second, but no, I got it right. Okay, so remember that. Then after pneumatics, we get into section 4. Oh, what? While I'm on it, dampers were another thing that were good for pneumatics, right? So you could do a VAV system off pneumatics. I've never seen one, but I'm sure they were out there a lot because you could do a VAV off of air pressure and change the damper position. Anything that can modulate like that is what was really, really cool for pneumatics. And I'll be honest, it's a cool system. The way pneumatics worked was awesome, but you know, uh, just got overtaken by more modern methods of doing stuff. I don't know. I've always had an affinity for old school ways of doing things, old school ways of controlling different stages of heat, like I was talking about when I had to deal with the multiple thermostats, pneumatics, having no circuit boards where everything is separate relays and older furnaces and stuff that controlled those sequences of operation. I love that just because it helps you understand what the more complicated things are doing, and um, it's hard to just teach that without getting to work on it. You know what I mean? It's hard to sit down. It'd be nice to have a furnace from the 1970s or 80s that was all mechanical controls, or to set one up that's all mechanical controls, because seeing all those separate mechanical controls work tells you basically everything that's happening in a modern circuit board. Seeing how a pneumatic control system works helps you understand what's happening with the digital side, because the digital sides are essentially doing the exact same things just through voltage instead of through a fluid. But I don't know, at least in my head, seeing those fluids moving is more enlightening or more easy to understand than trying to picture the little motors moving in different ways. I don't know. Maybe it's just me, but not having some of those examples, I think, I don't know, makes the concepts a little bit more esoteric or um, distant. Anyway, section 4. Any questions so far? I've been talking for a while. Um, Anything I brought up, you guys got questions on? We're moving pretty slowly through all this stuff. Hopefully we get through it all this class. Next class might be a review too. Maybe I'll have to make a video on it. We'll see. I still owe you guys a video. I haven't forgotten. You're gonna get something that you're gonna have to watch so we can make up that one. All right, section 4. Working on circuits and load components. I gotta open this back up. How do we want to get into this? Safety practices. You guys should know, hopefully, we discussed it a little bit anyway. Lockout, tagout, safety practices, things like that. Precautions when working on solid state controls. Most of your circuit boards and things like that, that's what they mean by solid state controls. So you have solid state devices, and solid state devices are extremely reliable. Okay, the reason we use them is because they are actually extremely reliable. So even though you see those circuit boards fail and things like that, usually the reason those things fail is some kind of design oversight from the manufacturer, or some kind of bad situation that those devices are in, something that's outside of its specifications, or some kind of other failure, overheating, which a lot of times is a design oversight. But the reason those boards fail, what I generally see, I don't know how many circuit boards you guys have done troubleshooting with before, but usually what I see when a circuit board fails is either a relay fail, and a relay is going to fail eventually. The set of contacts is going to get worn out. There's no way to avoid it. But the relay on the board will fail. So it'll either be a not very good relay, you know what I mean? Like a cheap knockoff relay instead of a nice one. Or it's just cycled too many times because something's wrong with the system. So that relay was cycling a lot, and that'll cause a relay to fail or a contactor to fail. And then the other thing that I see a lot, and it's something you should look out for, I don't see capacitors pop on boards that often, even though they can, really old circuit boards, usually the capacitor failing is what'll finally kill it. You'll have a capacitor in there that just bursts because capacitors, just like run capacitors, those little capacitors on a circuit board, can swell and go bad. And they get too hot, right? And they just break down. The dielectric in them breaks down over time. But resistors, I see a lot of brown areas on boards near resistors. Remember, all those little resistors on a circuit board are just little heaters. And, if there's design oversight on the board, or something just operated wrong, or there's not enough heat sink on the board or something like that, those resistors overheat and they fail. So look for that a lot. Especially, it's easy to see on those tan colored boards. I like those tan colored circuit boards because you can see those brown areas where everything's starting to get a little too hot. I don't see it as easy or as readily on the green ones for, whatever reason. But yeah, that's why those things fail. But remember too, that when you're handling them, you got to be careful handling a control board because the static electricity can cause issues when you're handling a circuit board. That's why they're shipped in those special packages to keep the static shock from damaging them. So always ground yourself to a piece of metal before you grab the circuit board. In my experience, is that as long as you ground yourself once, you're usually fine unless you're going to go walk across a carpet with just your socks um, on a dry day. Generally, I don't have issues with creating too much static electricity on a circuit board to where I've caused any damage. But they make grounding wrist straps to completely protect yourself. And if you're doing a lot of circuit board work, that's what they use. Is they put that little grounded strap and you hook that strap, the little wire lead coming off of it, to a piece of metal so that you stay grounded the whole time and you don't build up any static and mess up a circuit board. Goes through lockout tagout. We discussed that pretty good. More lockout tagout procedure. You should understand lockout tagout if you ever go work on a big job that's got high safety requirements, or government jobs, or I'm sure, guys that work for schools, very corporate environments. You need to follow those rules to a T, but you should still, even if you don't have to, you should follow them as closely as possible because they do keep you safe. And then it goes into talks about customer interviews and examination of the system, basic system analysis, and use of manufacturer troubleshooting aids. So this organized 4.2, so on page 42, this section 4.2 is a good thing to read and try and get ingrained in your head, is an organized approach to electrical troubleshooting. Especially what you'll find if you don't try to organize your approach to troubleshooting something, if you don't try and keep your methods close to the same every time, no matter what you're doing, you'll end up, you'll get pretty good at, hearing the customer complaints or whatever, or seeing what the system's doing and jumping into a conclusion of what's wrong based on that, and you'll overlook something else, and that's how you turn into a parts changer. I don't think we've discussed it a whole lot, but there's you guys were in John's class, so I don't know if he talked about what he considers the difference between a mechanic and a technician. That was one way he always tried to present it. As mechanics can change parts and technicians can tell you, how it failed, why it failed, and so on and so forth, was his way of uh, describing it. And that's not necessarily true, depending on how you use those words, but that's how he used those words. But being being able to understand why something failed, what made it fail, how to prevent that failure in the future, those are all very important. But just as important is having a good organized approach to doing your troubleshooting process so that you can avoid oversights that will, cause you to turn into a parts changer, um, inadvertently. Um, so make sure you double check the things you should. One good example in my head is, I ran into a couple failed boards, couple failed defrost boards in a row, and I had a system that didn't come on. So, I assumed defrost board's no good, things not coming on. That's the issue. I got Y coming in, but Y's not coming out. Another failed defrost board, need a defrost board, relays in it, no good, whatever. And, this is probably a year or two in the trade. And the system didn't have no refrigerant in it, man. You know what I mean? So low pressure switch is open. You're going to make those mistakes at some point. You're going to assume something's wrong without double checking everything else. And you got to try and do your best to organize your approach so that you don't do those things. So this is good way. This is a relatively good introduction into that, where in section 4.2. But the biggest thing is trying to understand what works for you and what your approach is. Like when we talked about sequences of operation, my method of checking low voltage first so that I can verify stuff before it. If you got 24 volts, it tells you high voltage is coming in. It's getting to the low voltage side. We've got low voltage, so I know everything before that's good. So it's a good place to start to make sure I'm not looking for a problem on my power side or something. Generally speaking, as long as you're pretty careful about how you approach it. Just things like that, having a method to where you go through and check stuff, and honestly, just being very thorough, not only looking for the first problem, checking for other problems while you're troubleshooting so that you don't miss things that could have caused that problem and things like that. And you'll get used to what problems cause what other issues and so on and so forth. But talking to the customer, 4.2.1 talks about this stuff too, and it's an important thing to keep in mind. Is a lot of the times, if you get pretty good at listening to what they're telling you, they'll describe what the issue is and where you have to start with it. Don't get me wrong, you get a lot of customers, that'll say, my thermostat's not working. And that's, of course, is my favorite example of, your thermostat's probably working. Okay, that's not the problem. But you'll get that, and that doesn't tell you anything. But, they might tell you, the heat comes on, but it only comes on for a second, then shuts right back off. You might have an issue. If we're talking about a furnace, it might be a flame sensor or something like that. Or, whatever, especially if you're dealing with intermittent problems, talking to the customer and getting a good grasp on what kind of problems they're seeing can help you hunt down intermittent issues. But a customer complaint is not going to tell you all the information you need to find the problem, but it will give you valuable information about it. It'll give you information about what the unit should be doing. Sometimes, the system might not work the way you expect it to work if you run across the oddball system or something like that. But it'll give you some clues. It just won't tell you everything. But it is a good place to start. Make sure you discuss what's going on with them. There's been plenty of times where I'm trying to hunt down a problem where if I would have prodded at the customer a little bit more, I know what I'm looking for. Sometimes they complain about something that's not even an issue. I've had at least a few times where people have complained that something's wrong with the heat pump, it's being noisy or something like that. And then you talk to them for a while and you figured out they just never noticed the thing going to defrost before. They happened to notice it going into defrost the other day. It went into defrost normally, and they just never really paid attention when it went into defrost, and they thought there was an issue because they weren't used to those noises coming out of the outdoor unit. Um, that happens. So talking to a customer and getting as much information as you can and listening will usually give you some very good information about what's going on, whether it be commercial or residential. You can get some valuable insight sometimes into what's working. And if you pay attention, you might be able to figure out if it's a non issue and be able to show them what happens normally and explain it's normal. Um, and you might glean insight into things, especially if you're dealing commercial. What's a maintenance guy might be doing wrong to create some of the problems. So they're all important pieces of information. So listening to the customer is a very good place to start on troubleshooting. And then after that, looking for all the issues you can and getting everything right. And then obviously use manufacturers' troubleshooting aids. That becomes more and more important each passing year because more and more things become specific to certain manufacturers, and you need to understand their system, or it's going to be difficult to troubleshoot. So manufacturers, I try and make it a habit almost anytime I'm working on something. If it's not just your basic standard run of the mill RTU or package system or whatever, um, if it's anything that has its own controls, I try and make sure that I know how to pull up that manual quickly. Getting good at looking for the manuals for units by searching the internet is really important. Um, you can use the internet to help you troubleshoot the right way, or you can use the internet to help you troubleshoot the wrong way. Your first source of information should not be the forums and things like that where people have had the exact same problem. That's kind of your last route. Like you've eliminated everything else. Has somebody else had the same problem so that I can figure it out by following their template? The right way to troubleshoot using the internet and using your phone as a helpful tool is to pull up the proper manuals, pull up proper procedures, pull up industry standard information, and use that as a starting point for trying to determine what's going on. But the most important one is manufacturer's troubleshooting information, whether it be service guides, wiring diagrams, their diagnostic procedures, whatever the case may be. Next questions. I think we're gonna be getting into motors next. Yeah, I think that's everything in here anyway. No. Are we still in the same section? This is section 4. Yeah, we're still in section 4. That kind of jumps to I guess it's going on for manufacturers troubleshooting stuff. All right. Fault isolation in the equipment problem area. So, after you use manufacturer's troubleshooting aids, what the book gets into is isolating it to a certain area that needs to be determined so that you can narrow it down to what's wrong. And that's, of course, an important thing to do, but that's all part of the process. And then 4.3, it gets into testing high voltage power. All right, testing high voltage power is pretty simple with a voltmeter. You should be able to do it. But understanding your voltage ranges is important, right? So when you're testing high voltage power, remember typically everything is plus or minus 10%. So, just because you're working on 208 volt, if you're working on 208 volt and you're only getting 200 volts, that's not very common. It's not very common to only get 200 volts, but it's still acceptable. Getting 195 volts on a 208 system is generally still acceptable. plus or minus 10% is fine. And 208, 230 volt stuff, right? 208, 240 volt motors have a pretty big voltage range, right? Because since they're 208 to 240 volt, you're plus or minus 10% of 208. So you're minus 10% of 208 and you're plus 10% of 240. So that range is everywhere from I think they got it written down for me in here. Yeah, 187 volts and 253 volts. It's a pretty big range. All right. Again, when you talk about motors and stuff like that, that voltage range isn't a very big deal depending on the motor design. It's going to affect how efficient it is. It's going to affect its life expectancy in whatever situations it's in. There's an ideal range of voltage for that motor, but they can work across a pretty wide range. When you're talking about lower voltage stuff, even lower voltage relays, um, you know, they honestly work it in even a higher range. So, a 24 volt relay should only be fed, 22 volts to whatever, minus 10%, whatever it is, you know what I mean? Minus 2.4 plus 2.4 in that 24 volts. But honestly, a lot of your lower voltage stuff will even actually work. Those relays will work down to like 17, 18 volts. It's perfectly fine. A lot of those things are made to work over wide ranges. But when you're testing high voltage, especially motors, it's going to be plus or minus 10% of the rated voltage or the rated voltage range. Now, remember, phase imbalance is different. All right, voltage phase imbalance, which is what 4.3.2 starts to talk about, is not plus or minus 10% on phase imbalance. Your phase imbalance should be only about 2% or less. So if you get more than 2% of a phase imbalance on a three-phase system, you have a problem. It can start at, plus or minus 10% of the actual voltage. So 480 is 480 could be as low as let's just do the math right here. 480 minus 48, I think 432. Yeah, 432 volts. It can all be 432 volts coming into a 480 piece of equipment. That might be perfectly fine. But you can't have 430 on one terminal, 470 on another terminal, and 510 on another one. Nah. It's plus or minus 10%, but you don't have the correct balance. You don't have balanced phases. So phase imbalance is not plus or minus 10. That's plus or minus 2, but the voltage itself is plus or minus 10. All right. Oh, oh yeah, here you go. Then it goes into, so that's important, understanding voltage, phase imbalance, voltage ranges. Fuse and circuit breaker checks is just continuity. So hopefully you guys got that down. And that's not too complicated for you. But you should understand how to do fuse and circuit breaker checks. And I think we discussed that briefly as well. 4.4 control circuits and low voltage power sources talks about isolating a faulty circuit, isolating inverse the pop using the process of elimination. So trying to narrow it down, make sure this thing's okay, this thing's okay, this thing's okay. So eliminating everything you can until you get down to the faulty component. Isolating a faulty component. So, as you narrow down where you're at, you want to isolate that component and check it. So, a good example, an every day, you should be doing this all the time example of, isolating a faulty circuit component and verifying that that's the issue. I am anal. I don't know why. I just am. But even if I know a fuse is bad, right? I can check voltage on one side, the other side of the fuse. I know that that fuse is no good. I will still check the resistance after I pull it out. Even if I know a compressor is bad, right? There's an issue inside the winding of a compressor. I've isolated it. I know it's doing whatever it is. I will make sure I understand which winding failed and what occurred. I make sure that I've tested everyone, I've checked everything, and I know exactly what winding failed and how it failed, whether it's open, shorted, or whatever. I don't just condemn it because it's automatically tripping the fuse. I know it's bad because it's automatically tripping the breaker or whatever, and it's probably got a shorted winding or whatever the case may be, but I make sure that I verify exactly what's wrong with it. And that's an important thing to do. Verify what it failed, how it failed, so on and so forth, just like I mentioned earlier. But isolating the component, all that, basically all of 4.4 you should probably read a couple times and make sure you get a good grasp on these basics. I mean, if you guys want me to, we can even go through this again. I don't think we actually just read through that section and went over it in class. But if you guys say, hey, I want to talk about all these winding checks and stuff again, this all goes into individual components, and these are things I wanted to go over. But I would read all of 4.4 again because I can tell you right now, there's no questions on your test out of 4.4, but it's probably one of the most important sections. All right, I would read all of 4.4 a couple times just to make sure that you've got a good grasp, because textbook ways of electrical troubleshooting are all extremely important concepts to have down, and probably the most common one that guys who just aren't very good at troubleshooting get wrong. Troubleshooting voltage to ground all the time. It's a bad idea because it can get you into trouble. Not using the hopscotch method of going through a control circuit. We talked about that a little bit in one of the first classes on this module. Is a bad way of getting yourself in trouble because you end up thinking something's wrong that's not wrong. So I would highly recommend you guys read through that again, and 4.5 too, for that matter. 4.5 is also important, resistive and inductive loads, but 4.4, I would go through that again. And like I said, I'll be more than happy to do a class just reading through that section and giving you my inputs on it. Might be something we can do. Resistive and inductive loads. I mentioned this earlier. You have resistive loads and inductive loads. Resistive loads are like your electric heaters and resistors, crankcase heaters, things like that. Inductive loads are things that create a magnetic field. Okay, so inductive loads, the most common one's going to be a motor or a relay coil, something of that nature. Resistive loads follow Ohm's law. You should be able to predict voltage, amperage, and resistance with just two of them there on any electric heater, water heater element, whatever. And if it's a resistive load, if it's just a straight resistance, if you have a resistor, you can figure out the voltage drop across it. You can figure out how much amperage, how much current's going to flow through it. All that. Ohm's law sets the rules for anything like that. Inductive loads, anything that creates a magnetic field, those are going to be different. Okay, you can't use the amperage that a motor pulls and the voltage that's applied to the motor to predict the resistance of the winding, because the amperage, the current flowing through it, changes as the magnetic field affects everything and as it gets up to speed. And it's a difficult concept to go over, but just the most important thing to remember is that if it's a resistive load, then Ohm's law holds. If it's an inductive load, Ohm's law still holds, but you got to be a lot better at Ohm's law and understanding the intricacies of how an inductor changes the behavior of an electrical circuit. So unless you're going to get really deep into electrical circuits and get electrical engineer level uh, um, knowledge, then it's just important to understand that when it comes to motors, you need to have the manufacturer's information to determine what the winding resistance should be, which can change based on temperature also, and what the amperage it's supposed to pull, and all that nice, neat stuff. But yeah, motors, solenoid valves, relays, anything that has to do with has a coil essentially is going to end up being an inductive load. I don't want to say coil because people think of heat coils as heat coils, right? But anything that creates a magnetic field is going to be an inductive load. Anything that's a straight resistance, like heaters and stuff like that, that's a resistive load. All right. Open, short, and grounding checks. Start and run capacitor checks. Start relay checks. We really got to go over. I really got to get this in next class. Hmm. All right. We will discuss troubleshooting capacitors. How do they do it? I haven't read through how they do capacitor checks. We talked about the motor stuff, so identifying unmarked terminals on a PSC motor. If you paid attention in the Fastco motor guide, you can deduce that. It's not the most important thing to be able to figure out, but it is nice. We talked about open, short, and grounding windings a little bit. We haven't really gone over start and run capacitor checks. So there's two methods of doing start and run capacitor testing. Or run capacitor testing. Let me start there. So there's kind of two methods of doing run capacitor checking. To start, it's going to be a little harder to use this method, but with run capacitors, it's pretty easy. So the methods of checking a run capacitor, the methods of checking both, I should say. And remember, if a start capacitor has a resistor wired across it to drain it, you see that a lot on train start capacitors and train equipment, but you could see it anytime. They put that little bleed resistor on it just to bleed the capacitor when nothing's running. If you've got that, that'll mess up these tests. So you can't have that resistor on there. You'll have to clip it. Honestly, you can just clip it off and throw it away if you really want to, but it's nice to clip it and then get it back on. But you can check the resistance across it, and what's going to happen is it should start at basically at zero resistance, and then it goes to open. Okay, so it'll start at zero, and if you got an old analog meter, you can kind of watch it. You go across the capacitor, and it starts at very little resistance, and then the resistance increases. And then if you switch the leads, it'll do it again. And that's what should happen with the capacitor. And if it just stays open, then it's bad. You know what I mean? If when you switch, no matter what you do, you don't get any resistance, it's open, it's bad. And if it stays shorted, it's bad. The resistance of a capacitor should change as you switch the leads if you're checking resistance across it. So it shouldn't just be open. It shouldn't just be shorted. The other thing you can do is look for bulging and things like that. Any amount of bulging, expanding on a start capacitor, it's got that little cap where the stuff will blow out of it. On a run capacitor, I've seen them explode, but usually they just blow up. They just kind of swell. Anything like that tells you if they're wrong. There's something wrong with them. What else? And then the other method is just checking it with a meter, right? Pulling it off, using the capacitance setting, and checking the actual microfarad value. Now, one of my favorite ways to test a capacitor on a run capacitor is under load. And honestly, I'll have to, let me see if I got something I can pull up on it real quick. I know. We'll do it some other time. I'll give you guys the formula. I promise. I'll give you the formula at some point. Check it a run capacitor under load. But that's the other way to do it. I don't think your book doesn't tell you how to do it. I'll tell you how to check a run capacitor under load. But let me pull up a diagram for it next class or something. With start capacitors, you have to check the capacitance. But the other thing that's important about start capacitors is the relay, okay? Because a start capacitor cannot stay in the system for more than a very short period of time. Because what a start capacitor does is it basically increases the power delivered through your start winding. All right. So the windings get hotter while there's start capacitors in the system because it draws more current. Basically, a capacitor is going to limit, and this is a little simplified, but a capacitor limits the available current to the winding. If you go back on those motors in that Fastco motor guide, you'll see it's the power is connected through that start winding through the capacitor. So the size of the capacitor is what dictates the current that is available to that winding. So if you have a lot of capacitance on that winding, it will be able to draw a lot more current. So when you use a start capacitor in a system, basically what it does is it gives a lot more current available to that winding than is otherwise available with only the run capacitors in the circuit. Okay? So if that start capacitor is in the circuit for too long, it's going to kill the motor. The winding is going to overheat. It's going to draw too much current and it's going to die. All right? So it's important that you have some method of pulling that start capacitor out of the circuit by the time it gets to about 75 or 80% of its rated speed. So basically, after a couple seconds max, 2 seconds, I think, is the longest you'll ever see a start capacitor in a circuit. And those relays, if they're failed in the closed position, then you're going to burn up a motor. The other issue you have with start capacitors is if the run capacitor is failed, but the start capacitor is good, the motor can kick on, the start capacitor comes out of the circuit, then the motor doesn't run right, and it shuts down, and then the start capacitor gets it going again, and so on and so forth. And the start capacitor will come in and out of the circuit too much. So I think I talked about it when we went over motors, but Amrad, who makes those turbo capacitors, has a capacitor now, a run capacitor with a compressor protection terminal, a CPT on it. And that basically makes sure that if the run capacitor fails, then the start capacitor isn't connected to the system. That's a very nice value. It's something that I wish they'd come out with a lot sooner to keep compressors and other things from being damaged from failed run, but good start capacitors. But aside from that, the start relay, you can have a couple methods of bringing that out, but generally it is a potential relay. Okay, even the cheap Super Boost capacitors, start capacitors that you can get have a relay built into them, a potential relay. And basically, once the motor gets up to speed, once that potential relay, once that motor comes up to speed, I'm trying to figure out how to explain it because it's kind of weird. You hit a certain voltage because of back voltage into the created by the motor. So you get this back EMF from the motor, and that causes a higher voltage. If you ever tested voltage at a capacitor, it's higher than the voltage coming in. So 240 volt motor might have 350 volts at the capacitor. So as that voltage goes up, as the motor gets up to speed, the relay pulls the start capacitor out of the circuit. So if something's wrong with the start relay, then it won't do that. It'll keep it in the circuit. But most potential relays also have basically a little timer built in that after a couple seconds, it'll take it out of the circuit anyway. So that's one way, is the potential relay. Then the other way, where's it at? Okay, the other method is a start thermistor. All right, so you can have a start thermistor in the system, which allows. Okay, no, this is completely separate. I don't want you to think this is the same thing necessarily. All right. So that's start capacitor checks and run capacitor checks. And I think we covered everything for the most part on that. You need to, when you're checking the start relay, no, we didn't talk about that. All right. When you're checking the start relay, you want to test the amperage going through the circuit, and you'll see the amperage spike. And if that amperage spike doesn't drop within so much time, then there's an issue there. I think that's really the only way to check. Potential relays, generally, I see them failed open, failed closed. I can't think of a situation in which I needed to really pay attention to how long it's in the circuit, because so many newer ones have the backup. They have that backup time delay in them. So it's pretty rare that you see it for way too long. But yeah, so that's start relays and run capacitors, but we'll cover those a little more at some point. Start thermistors, it goes into start thermistors in here, and there's a question on start thermistors in your exam. So you'll want to read 4.5.7 and understand start thermistors. I can't think of a situation in which I've had a start thermistor, but you could have one in a situation. So a start thermistor is going to change the resistance based on temperature. So just like any other thermistor, you'll have a positive temperature coefficient thermistor, and as the temperature goes up, the resistance goes up. So it'll allow current to flow through it until the motor gets up to speed. And as it gets hotter, as it draws more amperage, that resistor gets hot, and then you cut down how much voltage it's allowing to travel through the thermistor. All right, so it's an interesting way of getting starting torque to a motor. It basically works sort of like a start capacitor, but that's used basically to help start the motor. And if you look on page 59, the way the start thermistors in the system, the PTC thermistor, is just like a start capacitor. Start capacitors and any starting component is always in parallel with the run capacitor, because the run capacitor is always connected in parallel between the run winding and the start winding of a motor. And if you look at the compressor diagram, you can see you have your run winding, right? And then you have your start winding, and then you have your run capacitor in before that start winding. So power never goes straight to your start winding. It always goes to your start winding through a capacitor. And then if you've got a start capacitor or a start thermistor, it's just in parallel with the run capacitor. So they're basically in the exact same location. That's how they're wired up. All right. And that's one thing to remember. People think about run capacitors going to a run winding. No, run capacitors go to the start winding. So if you remember our motor diagrams and our motor information, hopefully you've got that down as well. So those are start thermistors, which is just another way of providing extra voltage to your start winding as opposed to just using a run capacitor in the circuit. A lot of people think about start windings as coming out of the circuit once the motor gets up to speed, and that's not really true. The start winding still gets power to it, but it's kind of better to think about it as an auxiliary winding. It basically keeps the motor running. It keeps it going in the direction it needs to. That's why some systems, some motors, depending on their design, if the run capacitor fails, it'll spin. It'll just spin backwards because the design of that motor is such that if the auxiliary winding, the start winding, isn't getting any power, the motor just spins the wrong way because it's got enough. The design of the motor allows it to run. It just doesn't allow it to run in the proper direction. So the start capacitor still gets bursts of voltage, and the start winding still gets power all the time. It's just that's the one that I don't know how to explain it. It's just the one. Think about it as the winding that gets it going and gets it going in the right direction. That's how I like to think about a start winding. It's not some winding that's only in the circuit for until it gets running, but it's one that keeps it going. It's more like it gets bursts of power, not that it starts and then it doesn't get any power. But anyway, remember start devices are basically always in parallel with your run capacitor. And we just got through about half the questions in the test. Half of what I wanted to go over. So I think what we will do is just continue this next class because I think even though it was a little jumping around, I think there was reasonably good information that we went over by just following this along. So maybe it'd be good just to keep following it along until we get the rest of the information that's on the exam through. I think that's a good way to spend the next class. So either a video, if I can find the time, I'll make a video going over the rest of this, or the next class will go over the rest of this, and that'll be the rest of the next class. And then maybe I'll shoot you guys a text, but maybe we can schedule your next exam for the week after that just to keep it consistent. But we'll see how that schedule works out. All right, so any questions? All right. I'm thinking so, unless you guys want to wait till just after. But I mean, it would be the 9th. I'm thinking aim for the 16th. See if we can do that just before Christmas. Basically, the week, aim for the 16th or that week for now on your next test. Or I don't know if we have class the 23rd. I'll have to look. I doubt it, right? Because we follow Fairfax. No, we only follow Fairfax for weather. We don't follow Fairfax for closures, I think. I don't know. I'll double check. But regardless, I think aim for the 16th. Probably avoid the 23rd since it's right before Christmas. It's less likely somebody's going to be there to moderate anyway. So I think aim for the 16th or aim for the 30th. Right? Is my thought. Yeah. Let me check. I'll see if we can just get it for the 16th unless there's objections. That'll give us between now and then to get over the rest of the overview and all that. All right, guys, got anything? Shoot me a text. Otherwise, that's the class for the evening. We'll go from there. Have a good night. So you should be on page 60 of your book at 4.6 on hydronic controls. So if you want to get to there, that is where we will start. You have an aquastat. Your aquastat is going to control your high limit, your low limit. Well, no, I shouldn't say that. Typically on a boiler, you're going to have a triple aquastat on most, especially residential, but even commercial settings, it's usually controlled very similarly, unless they're high efficiency boilers, which is a slightly different animal. But if you got a straight up boiler, a lot of times your aquastats are going to control the temperature. The pump will be going anytime. There's a few ways to set it up, but the pump will essentially run all the time or until you get no calls at all from any areas in the system. But typically, you're going to have a triple aquastat that's going to control your high limit, your low limit. So when the system has to come on and heat the water, even if there's not a call for heat, your high limit, which will shut it off if you reach a certain temperature, or if you go over a certain temperature, as a safety essentially, and then your pump controller. So it'll actually turn your pump on and off based on those conditions. But you can read through your section on an aquastat there. All an aquastat means is it's basically a thermostat that senses the water temperature to turn the system on and off, and it um, may also be a high temperature safety essentially. But typically, if it's going to be the high temperature safety, it's going to be the one that's mounted directly on the boiler. Um, Next section is a reset controller. Reset controllers are very important. 4.6.2. Reset controllers are important because they're becoming even more and more common nowadays, even on high efficiency systems. What you will do with a reset controller, the purpose of a reset controller is it monitors outdoor temperature, and it's going to modulate the boiler water temperature based on the outdoor temperature. So if you, outside it is 60 degrees, you don't need 180-degree water in the boiler system to provide sufficient heating capacity for the building. Whereas if it's 20 degrees outside, you may need 180-degree water or whatever your design temperature is on the boiler system to provide sufficient heating. So you're going to create a curve based on the outdoor temperature, and based on outdoor temperature, the boiler temperature is going to change so that you have enough hot water to meet the load, but you're not overheating water when it doesn't need to be as hot as that. So everything is less likely to short cycle, and it's a very good way of modulating capacity in a boiler system. So almost every modern boiler design, especially in a commercial setting, but even more and more common in residential settings, you're going to have some kind of reset controller to change the boiler temperature when less heat's required based on outdoor temperature. So that is the important thing to note. Remember that the reset controller is just an outdoor temperature sensor, essentially. And let me make sure that that is essentially, yeah, monitors outdoor temperature. All right. A reset controller monitors outdoor temperature. 4.6.3 low water cutoffs. Low water cutoffs are required anytime you have a boiler system. I was just looking at the text there. All right. Else is about to jump in. That's cool. Anyway, low water cutoffs. Low water cutoffs, if you look in the code book, if you ever read the mechanical code, low water cutoffs are required for every boiler system, period. The only way you can get around not having a low water cutoff is to have a flow switch on the system so that it monitors that there's actually flow through the boiler. They will generally accept that you not have a low water cutoff as long as you have some sort of flow switch. But you have to have some kind of safety that ensures that there's water in the boiler and that it's going to operate safely. So a low water cutoff just monitors a minimum safe water level in the boiler so that it doesn't operate when there is insufficient water in the system. With hydronic systems, with water, that if there's not enough water, you can start to create steam in the boiler, and that's not good if it's not set up for steam. On steam systems, it can just cause overheating because there's not enough water there to maintain a safe operating condition. So that's the purpose of your low water cutoff. We won't talk too much about circulator pumps. That should be relatively simple. I've got a class up on my other class on sizing circulators. You can go through that if you want. If you don't want to go through that, you can. Taco has a great guide on properly sizing circulators that works in a variety of residential and light commercial circumstances. I'd highly recommend you check that out at some point. Taco's guide is very good, but circulator pumps are circulators. Um, there's a difference between a pump and a circulator. And really, the only difference is its usage. But a circulator is going to circulate the water throughout the system. Zone valves are there to control zones. Just like a zone damper, a zone valve is going to control water flow to any individual zone with the thermostat so that only the ones that are calling for heat get heat. And then there's a thing on zoned hydronic system operating sequences here. You're more than welcome to look at that. You're more than welcome to look at that so that you understand the operating sequence. But it's basically boiler maintains required temperature in the water system. If a zone is calling, zone valve opens. Water goes through the zone until the zone stops calling. Zone valve closes. Boiler system maintains operation. It's the usual sequence of operation. Doesn't mean that that's the way it's set up all the time. Doesn't mean that that's the best way to set it up. But that is generally where you are at. All right. All right. And this is just for those of you jumping in. The next thing we're going to hit is section 5. So we're basically done with section 4. The only thing I want you to note out of section 4 is I want you to read and understand section 4.6.2 on reset controllers. A reset controller is an outdoor temperature monitor, essentially. Reset controller monitors outdoor temperature to maintain boiler system temperature. That's the most important thing as far as your exam goes. Everything else is for your information. Now we are on variable frequency drives. So variable frequency drives, let me check what we got to go over. All right. So when we get to, well, going to be pretty close. All right. On variable frequency drives. Variable frequency drive, if you remember from our class on it, its purpose is control the speed of the motor. Generally going to be used in blower motor situations and in head pressure controls. That's your most common applications. Doesn't mean it's the only applications, but your most common applications. Most common applications are to control the speed of the indoor fan motor on variable, usually VAV systems, but there's other situations as well. As a matter of fact, they're becoming standard on all RTUs really fast. Pretty much anything over 5 tons is shipping with VFDs at this point, it seems like. But even if not, for variable air volume systems. They're critical on the indoor fan, and they're very good ways of controlling head pressure on low ambient temperature situations. So those are your most common applications, but there's other applications besides that in which you'd use them. And there's plenty of applications all over the place. Pumps, large pump systems, any large motor is typically going to be controlled by a VFD at this point. But in HVAC, those are the most common places you run into them. So that basically covers the first part. Who's in the waiting room? Oh, got it. All right. So, talking VFDs, again, just to cover it one more time, you're going to get controlled starting, controlled acceleration, adjustable operating speed, adjustable torque limiting, and controlled stopping. Those are all the benefits of the VFD. The primary thing that they get popularly used for is the adjustable operating speed. That's its primary purpose. Everything else is generally just an extra benefit that comes along with it. So, talking VFDs on page 65 on 5.1.0, basic VFD operation. I want you to understand the difference between PWM and analog SCR rectifier VFD units. It was not that long ago when your SCR units were your primary ways of controlling VFDs. The problem is they're a little bit more prone to failure. VFDs, there's a lot of complicated things going on inside of a VFD, and it wasn't that long ago, even 10 or 15 years ago, that these things were relatively prone to failure. So you wanted to be real careful about the applications you put them in and how you utilized them to minimize its possibility of failure, primarily from components overheating and things like that. If the fans aren't working or the heat sink's not beefy enough, you got transistors and stuff in there that like to blow. All these solid state components still get hot. All right. Solid state is in general more more what's the reliable than your even older school ways of doing things, like controlling a motor through a potentiometer or something like that, a varistor, but it's still going to fail. Nowadays, almost everything is microprocessor based PWM, pulse width modulated, and you're going to see that term tons and tons and tons in the trade. Pretty much everything as far as mini splits, VRF systems, your building control systems, everything sends pulse width modulated signals to send basically different voltages for different situations that it's trying to achieve. So most of your VFDs these days are going to be pulse width modulated as far as how they send the signal, how they control the speed of the motor. It basically takes that signal, turns it into DC, chops it up, makes it look like an AC waveform, and sends it out to the motor. Okay. And that is way more reliable than analog SCR rectifier VFD units. All right. And the biggest deal with that, the other good benefit that you're going to see out of that you want to get to, and I'm trying to find the exact spot where it says it, but I just want you to remember that you will have reduced problems with harmonics when it comes out of those two. So dirty power problems. There you go. Second paragraph down, it talks about dirty power problems and harmonics and electromagnetic interference. The SCR units were more prone to that than the PWMs. But I can tell you that aside from that, the PWM units tend to be a ton more reliable in general than the older VFDs. So that's something to keep in mind as well. You see an older VFD fail spectacularly. It wasn't something that's very uncommon, and it's probably why you don't see many older style VFDs around even now. The VFDs that were built in the late 80s, early 90s were really prone to failure, and then throughout the 90s and the 2000s, they're still somewhat prone, and now we're pretty good to go. They're extremely reliable at this point. All right. What else? We go through that. You can read more about the inverter sections and all the sections on VFDs. We covered that a little bit already, so I'll skip the rest of it. Go to section 5.2, programmable VFD parameters. We talked about it. There's tons of parameters that can be programmed in a VFD. You want to make sure that you understand the parameters when you're changing them. Typically, you're going to maintain the same parameters when you're switching out a VFD. But we also had somebody bring up the fact that can sometimes be a problem too. You really want to make sure you understand what's going on when you're putting in a VFD. If you are unsure, you should probably contact the manufacturer and make sure what settings were used on original installation and or is recommended for the replacement VFD. It's something I generally recommend to people. If you're not sure about how to set up a VFD, get an OEM VFD. If you're lucky, it'll already be set up for the situation. If you're not, at least you have some kind of fallback to get some tech support on it. Other than that, the control panel is typically, all right, the control panel is typically going to be removable. The benefit of that is what we talked about is that you can take that control panel off of an existing drive, and if you're putting the same drive in, you can put that old control panel on the new drive and upload all the parameters from the old drive to the new drive. That's your primary benefit from having that removable control panel. All right. That allows you to save the parameters from the old one, put them in the new one, and everything should operate the same as it was before if everything is wired the same and there hasn't been any revisions in the firmware or anything like that in the VFD. Typically, that's what you're going to do is remove that old one, put it in the new one, and then you can put the new control panel on if you want and download from the VFD in that control panel, that new control panel, so that they'll still have a new control panel on it. But just remember that a VFD control panel is typically removable. All right. What is this? Moving on. Okay. what you'll need to do is you'll need to look through these parameters and understand what the parameters that you can generally change in a VFD are. So you have minimum and maximum frequency, acceleration and deceleration, current limiting, volts to hertz ratio, which is going to control whether or not you change torque. When you're changing the speed, you have volts to hertz optimization, nominal voltage of the motor, nominal frequency of the motor, nominal speed of the motor, nominal current of the motor, supply voltage, basic frequency reference, and did I miss anything? I don't think so. But regardless, read through all those parameters. Most of them have to do with the actual motor that's installed. So there could be a situation in which you swap out the motor and some of these values need to change for whatever reason. In general, your new motor should be of almost the exact same specs as an old motor, but in case they're not, you may need to make a couple adjustments in the VFD to make sure you're not creating a bad situation. But typically, it's the motor specifications. Essentially, you're telling the VFD so it knows not to exceed certain limits when it's dealing with that motor. So the speed of the motor, the current of the motor, the voltage of the motor, so on and so forth. You don't want to exceed those parameters, and the VFD will make sure it limits itself to what the motor can handle, which is really nice, right? And it'll also, the nice thing about VFDs is they help protect the motor so that if there's a voltage spike or something like that, the VFD will typically shut down instead of run that motor and cause a bad situation. Other than that, it's just the frequency and the voltage is what you're changing up in a VFD. So the frequency and the voltage. Oh, somebody just got in the waiting room. Okay. So the frequency and the voltage is typically all you're going to be able to control outside of the current and how fast and how slow it starts up and slows down. Basically, starts and stops. So good examples of what a VFD can control is minimum max frequency, acceleration time, and the current limit. A bad example would be something like service factor of the motor, power factor of the motor, um, RPMs of the motor, right? Even though it's going to change speed, you can't change the max RPM. You're not going to get an 1800 RPM motor to go 3600 RPM, things like that. So hopefully that makes sense. Basically, understand you can change the frequency, you can change the voltage, you can change the current limiting, you can change the acceleration, you can change the deceleration. You can't change the inherent characteristics of the motor through the VFD, something like power factor. That's going to be dictated by the motor itself. All right. The next question that we have to meander our way to is in section 5.3.1. So basically, next section. So 5.3 VFD selection characteristic or considerate VFD selection considerations. All right. When it's selecting a VFD, the primary thing you have to think about at all times is that the VFD is rated for the motor. All right. So the VFD needs to be able to handle the horsepower of the motor. The VFD needs to be able to handle the voltage of the motor. The VFD needs to be able to handle how many phases the motor is. Which is typically going to be 3 for a VFD anyway, but has to be able to handle the maximum current through the motor. So you can't use a VFD that's rated for 5 horsepower on a 7.5 horsepower motor. In general, you want to be the same with the VFD or oversize it a little bit. That's the most important thing, that it's rated for the current and the horsepower. Those are the most important things to line up. In general, 5.3.1, looking at 5.3.1, VFD operated motors. Those are going to be NEMA Design A or NEMA Design B motors. And I also mentioned in the class on VFD, something to bear in mind is that grounded shafts are becoming more and more recommended on VFDs because the stray voltage is essentially, there's a better way to present it, but essentially the induced current from the VFD can cause issues in the motor shaft, which can break down the bearings. So you try and eliminate those by grounding the shaft of the motor, and that helps avoid bearing failure. So the NEMA design is important to kind of have in the back of your head, but what you kind of want to remember in the field is that the motor has to be rated to be used with a VFD. So you want to have essentially the exact same motor, verify that it's a drive rated motor, and you probably want to select one with a grounded shaft if at all possible. Those are kind of your 3 extra things you're looking for if you're getting a motor for use with a VFD and you're just making sure that is correct. If you're using a motor other than an A or a B, see if I can find what they're getting at. What? The heck? Sorry, I'm just looking here to make sure I understand this question. Okay. If you're using a VFD on a motor that is not a NEMA Design A or B, you're going to have to make sure that the drive has special circuitry in it to handle the situation. Can't give you any field experience on that situation at all. I've never used a motor that was not intended to be used with a VFD. And I would obviously, if you're going to be putting it in that situation, you would definitely want to consult your VFD manufacturer to say, hey, this is the motor I'm going to use. This is the VFD I'm going to use. Can I make these compatible? I would venture to guess 9.5, 9.9 times out of 10, the answer is going to be no, select a different motor. But with special drive circuitry, you might be able to make it work. So just remember, if you're not using an even design A or B motor with a VFD, there's going to be special drive circuitry needed to be able to control the issues that are going to arise when using incorrect motor with a VFD. Next thing is selecting your drive. We talked about that a little bit already. The environment of the drive. Remember that class I talked about the environment the drive is in? Make sure that the environment the drive is in is suitable for the drive. Oftentimes, rooftop units is not a great location for a drive. Even if it's in the airstream when that unit is in an unoccupied state, if it's not moving air, you could still end up putting the VFD in an environment that is not suitable for the drive. So pay close attention, especially if you're having drive failures or something like that. Pay very close attention to the environment the drive is in. Again, modern VFDs tend to be extremely reliable. So if there's a failure, it's just like anything else. If somebody's telling you they're getting 3 bad transformers out of the box from the supply house, it's probably not 3 bad transformers out of the box from the supply house. I can tell you, I have actually seen multiple bad relays out of the box before from, an equipment manufacturer. It does happen. You can have a bad run of some product, and it will surely be that all those parts have failed. But it's an extremely rare situation. It's probably something you will only run into once in your career. And as soon as you see the first failure out of something that's brand new or not of an age of which it should fail, then pay close attention to what factors caused it to fail. It's the same as that old saying, compressors don't fail, they're killed. All right? Compressors do not die, they are murdered. Most parts are murdered in some way. Most parts, if they're used in the situations they're supposed to be used in, they will either have a very long they will either have a very long service life, or they will perform essentially forever. All right, but there's always that point where it's past, what is it, 1,000,000 cycles or something, 100,000 cycles on a contactor. After that, contactor's going to fail. But if the contactors are failing every year, what's causing the contactor to fail every year? If the VFD is failing, going into some kind of error every month or two, what's causing it to go in that failure every month or two or every week or whatever the case may be? Pay attention to the environment and the selection when you're having lots of failures like that. Torque requirements, make sure that VFD can handle the torque. The duty cycle, make sure it can handle the duty cycle. Again, duty cycle is basically how often it's running. So something that has a 25% duty cycle basically should only run 25% of the time. It should be down 75% of the time. So you want to make sure that whatever you use has a good duty cycle. And honestly, most of the things that you're using in our trade should have a 100% duty cycle. It should be able to run continuously until the cows come home. All right. It should be able to run all the time. So you don't want to change out a drive with a high duty cycle with one with a smaller duty cycle. There's a reason some of these things are cheaper. All right. The two drives are not exactly the same. So a drive that has a small duty cycle might be made for something like an air compressor. You can you can feed a air compressor off a drive to get different pressures or whatever the case may be to maintain constant pressure output. That doesn't need to be 100% duty cycle because the compressor is not going to be on 100% of the time. But a VFD in a rooftop unit is going to be on almost 100% of the time. So you need to make sure that it's got a sufficient duty cycle. And then we get into dynamic braking. If you remember right, I told you dynamic braking was not something I wanted to get too deep into during our class. It is not it's not something that I feel like it's important to cover. I could be wrong about that. It could be relatively important in some situation in certain areas of the trade, but in general, I don't necessarily care how the VFD brakes. I just care that it brakes properly and it brakes in such a way as to not cause any harm to the motor. I'm not going to change a braking characteristic, and I'm not well versed enough in VFDs to tell you how to change how it breaks, or if you can change how it breaks, and so on and so forth. All right, but what I do want you to know under 5.4 is that the most common the type of motor braking that is often used with AC motors being controlled by variable frequency drives is going to be dynamic braking. So if you look down there, dynamic braking, DC electric braking, dynamic braking for AC drives, and electromechanical braking for other situations. Friction brakes are used for applications such as printing presses, small cranes, overhead doors, hoisting equipment, and machine tool control. But typically for HVAC, we're going to be using dynamic braking. So if you read dynamic braking of an AC motor in conjunction with dynamic braking with an AC drive, that should cover most of your braking situations for drives as we encounter them in the field. And that covers VFDs. Yep. Any questions on the VFD section? Hitting section 6. So we are now on page 75. Hitting section 6. We are going to be talking about ECM motors. You should be intimately familiar with the operation of an ECM motor. It is an extremely important thing to understand because they are slowly phasing out PSC motors for all but the smallest circumstances in our trade. So for inducer motors and, things like that, you'll still see PSCs. You'll still see PSCs on older equipment and on replacements, but ECMs are becoming the standard for your small blowers, even your smaller rooftops, 5-ton. I think I've seen an ECM on up to a 7.5 or 10-ton rooftop, an ECM blower. So your rooftops that don't have three-phase motors will probably be ECM motors. Your residential equipment is all moving to ECM motors. Even I am starting to change out PSCs for ECM or ECMs for PSCs in replacement situations because it's a little easier to stock a single ECM even than it is to stock a PSC. And it's a little bit of an upgrade, right? Typically, you're somewhere around a half a C or something like that, just going from PSC to ECM because the PSC is 60% efficient and ECM is typically closer to 80% efficient. So there's tons of benefits to ECMs. They're becoming the standard for most situations where you would use a PSC motor. So you're going to be troubleshooting them more and more and more if you do any type of service work. You're going to be installing them more and more and more if you do any type of installation. Even if you do commercial on your smaller units, you're typically going to start seeing ECMs on your condenser fans and your smaller blowers. I wouldn't be surprised if they start making more headway in exhaust fans because I'm starting to see exhaust fans with variable speed ECMs in them instead of trying to control the output with a belt. So instead of doing belt drive, you're starting to see ECMs with variable speed controllers in them for exhaust situations. So it's here to stay. It is here to stay, and you have to learn everything you need to do to install them and troubleshoot them. So ACM is basically you're going to have a motor control section on the motor. It's an electronically commutated motor. You're going to have a motor control that's going to essentially take the single phase power coming in, turn it into three phase, and send it to what's essentially a three phase motor section on the other side. So if you're troubleshooting the motor section of the ECM, it's exactly the same as troubleshooting a three phase motor. You got to have equal resistance in all three of the windings. You should have no shorts, no opens, no shorts to ground. All right. It's extremely simple to test the motor section of an ECM because it's just like troubleshooting three phase motors, which is probably the easiest motor to check because you're basically just comparing the resistance of the three windings and making sure they're the same. No big deal. The control section is a little bit more complicated because there's no real way to test it except for to feed it what it's supposed to be fed, and if it don't work, it don't work. So it's just like troubleshooting a simpler control board. You make sure it's got all the signals it's supposed to have. It has high voltage coming in. It's got a 24 volt or whatever the voltage signal is on a condenser. It still might be a high voltage signal to the control section, or on your blowers, it's typically going to be a 24 volt signal to the control section that's going to tell the motor the speed it's supposed to run at. If it's got a speed signal and it has power coming in, which is supposed to be in it all the time, and it doesn't run, the controller has probably failed. First, you verify that the motor has not failed, and if the motor has not failed, then it's definitely the controller. If the motor has failed, then the controller may be good, but typically, anytime you have a motor failure, they recommend you replace the controller anyway because a motor failure could cause problems in the control circuit. So it's kind of a catch-22 anyhow, but I still recommend that you generally verify which part of the motor failed, whether it be a mechanical failure or an electronic failure, whether in the motor control section or in the motor section itself, so that you understand what the failure was, so that you can try and look for problems that may prevent it in the future, whether it was a voltage surge that hurt the motor control section or was a bearing failure. So typically not a whole lot you can do about those, but you can pay attention to the operating conditions of the bearings and what type of bearings are in it and all that. So that's the quick overview on ECMs real quick. Understand that you have multiple connectors on an ECM. So you have, looking at section 6.1, if you read through, you should be able to find it. See if I can find it real quick. We're looking what the 5-pin connector is for. All right, we want to make sure we find it in here. Actually find it in the book, because you're going to have a 5-pin connection and a 4-pin connection typically. Some ECMs, if they're especially the variable speed ones, the earlier variable speed ones, you would have a 5-pin connection and a 16-pin connection. So in here, 5-pin, where is the 5-pin? The note on the 5-pin connector. All right. All versions contain a 5-pin connector where power is applied. All right, so that would be the third paragraph. So you have the first one under 6.1, second one, and then the third one down. So the first paragraph moves on to the other side of page 75. Then you have the second one, the third one down. Basically, Gentech is who makes all your ECM motors. I think they're owned. No, not Gentech. Regal Beloit. Whoever writes, who the heck writes the ECM motor guide? Because I think they got sold, right? I forget this sometimes. ECM motor guide. I got dealer toolbox. Yeah, Gentech. I had it right the first time. So basically, Gentech is who makes almost all the ECMs that are in service. There's a couple other manufacturers making aftermarket ECMs. Gentech makes the Evergreens, and then Mars is making a retrofit ECM that's kind of interesting, but I still tend to prefer the Gentechs. Doesn't really matter though. Use whatever you like. But Mars and Gentech are the two biggest ones I see right now. Um, so Gentex always have the 5-pin connector. I think basically everybody utilizes the same style right now, except for on commercial equipment. And that 5-pin connector is where the power comes in. So it's typically set up for a couple voltages, and that's where your power comes in, and it stays on. The power stays on into the unit at all times. So the power will be on that ECM motor at all times, whether it's running or not. It starts running when it gets a control signal, but power is at the motor at all times. All right. So 5-pin connector, input power voltage is what that's for. All right. ECM motors sequentially energize the windings to provide rotation. All right. So, like I said, it's basically a 3-phase motor and set up just like a 3-phase motor. So it sequentially powers those windings to get the motor operating. So instead of having a start and a run winding, which dictates that motor rotation, it actually powers windings at different times, and that's what makes the motor rotate. You have a north and south magnet on the rotor, and as the winding energizes, it attracts that magnet and it causes rotation. So sequential energizing of ECM motor windings provide rotation of the rotor. That is also in section 6.1. And then what does the presence of 4-pin connections on a ECM signify? You will want to pay attention to what a 4-pin connector means. That is your newest version of a PSC motor. Yep. So the older ones had 16-pin connectors. These days they've dropped that down to basically just 4 pins. And as we're talking ECMs here, just to clarify, there's basically two different grades of ECM, and people get them mixed up sometimes, and even I do when I'm talking about it as I'm reading through this section. You have an X13, all right, which is a constant torque motor, and that is one that you would use to replace a PSC motor. And then you have your actual variable speed ECMs that their controllers are complicated enough that it's matched with the equipment that it's being used on, so that you can maintain a certain speed or maintain a certain airflow rate based on what's going on with the system. So when we're talking about these 16 verse 4-pin connectors, if you look on page 76, between the ECM 2.3s and 2.5s and the ECM 3.0s, those are your true variable speed ECMs. Those are the ones that get matched to the system, and you have to be OEM motors when you replace them, as opposed to the X13, the constant torque motors like the Evergreens and the Mars Azure ones and things like that, where you can retrofit them into other systems. So try and remember that, especially if you don't work on ECMs a lot. Try and remember that there's a difference between those X13s that get that 24-volt signal to the other pins at the speed selections, and there's typically 4 speeds to be selected, but there's 5 pins available. And then your actual variable speed ones that have to be matched with OEM equipment, and those had 16-pin connections in the past, and they now have the 4-pin connectors on the newest version of those ECMs. All right. Checking the windings. We talked about checking the winding resistance on ECMs. What we got next? We got speed control. All right, yeah, no, let's go through this section a little bit first. All right, the speed control of an ECM is controlled by the electronics in the motor control section, and it's also controlled, it's intrinsically linked with the motor, the control circuit, the control board. The ECMs are programmed to match up with the control board of specific equipment and the cabinet sizes and things like that. And I think it's way less complicated than they would make you believe if you sit through a manufacturer's class on it. But the point still is that an ECM motor is programmed to be with a certain piece of equipment, and replacements have to be programmed like that. Essentially, the motor monitors its operating characteristics, and it knows what kind of CFM it's putting out based on that, and it speeds up as necessary to put out the CFM desired or set it what it's set to inside the system. But most of it is done internally to the ECM. Everything else is just signals from the circuit board to make sure that it's matched up with the equipment it's working on. So you can read through that section some more, but ECMs are speed controlled basically internally. ECM installation and setup, follow the manufacturer's instructions. All right. If you're putting in an ECM motor on a piece of equipment and it's an actual variable speed ECM motor, then make sure that you follow the original equipment manufacturer's instructions. If it's an X13 or it's a replacement motor, make sure you follow the manufacturer's instructions for that. Make sure that it's matched up with the type right application. But I'm not going to read through ECM installation and setup a whole lot because you should be reading the original manufacturer's literature every time you're setting up one of these motors, period. No ifs, ands, or buts. That is your job. All right. So you can read through that section, but my advice is read the motor installation requirements and read Gentek's ECM service guide so that you can properly understand that information. Motor troubleshooting. Again, we've already discussed it at length. Your troubleshooting boils down to removing the controller from the motor, testing the motor to make sure it has not failed, checking out whether it's mechanically failed, you moving the shaft back and forth, spinning the shaft, making sure the bearings are good, and then making sure that the proper signals are applied to the ECM motor and testing those signals and seeing if the motor operates when those signals are applied. If it does not operate when those signals are applied and the motor is fine, the windings check out, then the controller has failed. If not, then the motor may have failed. The other possibility you'll run into is the circuit board for the equipment has failed, sending the signals to the ECM. But part of making sure that you have the proper signals to the ECM is understanding what signals are being fed from the control board of the equipment to the ECM motor. You need to read the original manufacturer's literature to determine what pin you should test and what voltage should be there. They do make a service tool for testing ECMs. You can look into that. A lot of the times it will not work with all ECMs, but it's getting to the point where their service tools will basically work with all of them, so you should be fine. But always read the original manufacturer's literature when troubleshooting an ECM. There's really no way around that. Always double check. Don't assume it was the same as the last one. Don't assume they kept using them the same way. Always read the troubleshooting steps from the original equipment manufacturer when troubleshooting a variable speed ECM. An X13 is really simple. It should have its control signal, its power signal. If both are there and it doesn't operate, then it's failed. You can go through the process of determining which component failed, but it doesn't matter. It failed. It needs to be replaced. So that is the primary thing I want you to get out of that. The other thing that you need to understand is the winding resistance to ground on an ECM. So if you're checking for a short to ground, all right. So you need, again, all three windings should be the same. Okay. All three windings should be very close to exactly the same in an ECM. All three windings should have the same resistance. If not, if one is open, you get OL. Then it is then that's an open winding. If you get dead short, you read 0 from one winding to the other, then there's a dead short on a winding. Checking to ground can be tricky, okay, because every motor is a little bit different when it comes to compressors, when it comes to ECMs, when it comes to three-phase motors in general. Every motor can be a little bit different on what its acceptable voltage or acceptable resistance to ground is. So looking that up is a good thing to be in the habit of, actually trying to find the details of what is an acceptable range of resistance to ground on this particular motor. is a really good habit to be in so that you get a feel for those situations. For instance, the old, and I can't even remember what they are because this is not how I troubleshoot, but you had an old rule of thumb with reciprocating compressors on what was an acceptable Megger value, what the resistance you could have to ground was on a reciprocating compressor. And when scrolls came out, that value dropped significantly. So again, I can't recall the numbers off the top of my head, and I won't lie to you guys and try and pull them up. But the point is that a scroll compressor can have a smaller resistance value to ground and still be perfectly fine than an older semi-hermetic reciprocating compressor could. So what might test as a fail on a recip will actually be a passing value for a scroll. So again, you can't assume that you know what the resistance to ground should be. And just because you have some resistance to ground does not mean that it is failed or that it does have issues in the windings, that the windings are breaking down. Those aren't necessarily true statements, okay? So you need to determine what the acceptable values are for the particular your motor you're working on. With ECMs generally, if you get anything less than 100,000 ohms to ground, then it's failed. If you get anything above that, then it might be fine. I would say, well, I don't have any personal experience, so I can't say. In general, I start to get a little bit scared if you get below 1 million, and I start to really get scared when you get below 500,000 ohms. You get below, 500,000 ohms, and I'm going to start questioning whether or not this motor is okay. But the technical correct value is that you should see no less than 100,000 ohms to ground on an ECM. So keep that in mind. All right. So that's on page 80. 100,000 ohms to ground is okay. Anything over 100,000 ohms to ground is okay. And that's it for ECMs. Moving right along. Doing pretty good. Any questions so far? Speak up if you got questions, man. Or if I said something wrong. Hell, I might have just lied to you guys about everything. Speak up if you got a question or something, or if you got input. These classes go, you know what I don't like about these remote classes so far? Is that I get a lot less, even less than I did before, and people would still stare at me blankly half the dang time where I taught a class. But even more so with these remote classes, you guys don't ask any questions. You sit there, I can't see your faces, and I don't know whether or not you're lying to me and any of this stuff is making sense. Because I can usually tell when I'm looking out in a classroom that, yeah, it looks like they're getting it. Or no, you all are staring all at me with a blank stare. That means you don't understand a damn thing I just said. I don't even think any of you all are in the class right now. All right. Okay. You say so. All right. Well, oh, crap. Oh, man. That's it. That is actually the whole exam. Everything we went through in these last two classes should have covered your entire exam. And if you paid attention to where I made particular statements about everything, you should be good to go. We covered your whole exam. I would highly recommend, again, I would highly recommend that you guys read through the stuff on troubleshooting components and troubleshooting circuits. What do they call it in here? I call it the hopscotch method. I think they called it something else. If you go back to module 2 on section 4, where was that at? Or did they? No, they really. Maybe I'm lying. Maybe I'm lying and they don't talk about it the same way. Anyway, pretty much everything in section 4, if you were to ask me what's the most important section out of this, it's making sure that you understand everything in section 4. Troubleshooting circuit and load components, everything in that section is probably the most important one to go through, double check, make sure you understand every single concept in that section. And that is when we do our first lab, when we get to there, which will hopefully be in the next few classes. That is what we're going to focus on, is stuff out of section 4 to make sure we understand how to apply the information there. Anyway, other than that, everything else is icing on the cake, and some of it you'll have to get through experience. You know, the VFD stuff, if you don't work on VFDs regularly, which I think most of you do. Most of you guys are commercial, and I forget that sometimes because I'm so used to having a class of mostly residential guys. But if you don't do VFDs a lot, it can be complicated trying to understand a VFD until you've messed with a few. Everything out of what I'm flipping through again. Section 2, all the stuff out of section 1 and 2 is still important, but to me, my philosophy has always been the basics are the most important thing. And if you understand the basics of troubleshooting circuits, then everything else should just be understanding the component you're working with. So I would highly recommend you go through that. And if there are any, I'm serious, any questions at all out of the information in section 4 or in this module in general, ask me about it. You know, you can shoot a group text in the class so the rest of the guys can get some benefit out of it. But anytime you got a question, if I don't know the answer, I will find the answer for you generally. So if you don't know the answer to any of this stuff in here or something doesn't quite make sense when you read it, then let me know and we'll go over it. I mean, otherwise, if you don't have any questions, that's all the stuff right in your exam. That's all the stuff we're going to go through in Module 2. I will verify that your exam is going to be next week unless there's any objections as of right now to it being next week. I will schedule it for Wednesday unless for some reason I can't get it, and then I will shoot you guys a group text and check if the rest is okay with you. After that, we will move on to Module 3, and in the meantime, I will start working on setting up our first lab so we can start troubleshooting some components just to get some hands-on on making sure we know how to troubleshoot some of the stuff that we went over so far. The next module is going to be AC. Oh, yeah. All right. So it looks like our next module is air conditioning. Easy peasy stuff I probably have enough stuff set up for already to go through relatively quickly. Refrigeration cycle operation and troubleshooting, we're going to run through that in no time flat. 2 or 3 classes max. We're going to go through that. I'm going to give you guys enough information to make your head spin. That is extracurricular. That's my own way of approaching it, and you guys can read the book by yourself. I will skim through the book to make sure I cover everything, and then we'll obviously review for the exam. Okay, but for the most part, I'm going to leave this book out of this situation. So module 3, 2 or 3 classes on it max, then we're moving on. Then we'll get into heat pumps, which is basically the same thing over again. We should get through that in 1 or 2 classes. Easy. Any questions? Troubleshooting AC is complicated. I'm not going to pretend like it's easy, but like I said, I've already got all the material put together for that. So it should be easy for us to just run through it, and you guys will just need to keep up if I move too fast. This is good. This is where I want to get to, stuff where I've already got stuff set up right, so that I can be ahead of the curve here. So our next few modules should go quick, and it's good because we need to, I think, because I think we're running pretty far behind. We kind of need to catch back up a little bit so that we can get through some of these more complicated modules again later, because it'll probably take up more classes than I'd like. Nope, it's not. I was saying at the beginning of class, I've already got my editing software open now so that I can pop in. I'm going to pop in last class and this class on the same video. So I'm just going to throw that in real quick. I'll text you guys when it's done, but it should be within the next hour or so. So last class and this class, I'll put up as one video. Module 2 review, and I'll throw that up and then notify you as soon as it is up. Usually takes about an hour for it to render and about an hour for it to go up. So probably late tonight. If it's past 9 o'clock, then I'll probably just shoot you guys a text in the morning. But if for some reason you don't see that text from me, ask me about it tomorrow. I'll make sure it's up. But like I said, I've already got it open, so I can throw everything in there. Biggest deal is making sure the audio is good. I might not even edit out the crappy parts. I'll probably just throw them both up, and you guys will have to skip through whatever silence I got in there. I'll edit the beginnings, but that'll probably be it. So I can get it up there quick, so you guys can listen to it all again and make sure that you know everything you should be reviewing for your exam, because I know that's important. Okay. All right. Well, I wasn't really planning on it, but I guess that's an early class unless you guys got questions. That'll give me some time to get that up. And then, like I said, if you guys got any questions, now's a great time tonight or sometime during the week to ask me questions if there's anything out of Module 2 you didn't think we covered good enough. But we basically went through the big spots and covered it all. So I'm not going to jump into Module 3 now. Maybe what I will do is try and give you guys some extra reading on troubleshooting AC to make up for the rest of this class. I'll get you a head start on Module 3, but focus on your exam for now and then do that later, because we'll probably still end up covering whatever I send you. So, yep, that's it. So, you got questions, shoot. If not, have a good evening, and I'll be in touch and let you know if for some reason next Wednesday doesn't work for you or I can't get next Wednesday. We'll discuss other options on the group text. All right, guys, have a good one.